Thanks for coming. This is the tough slot. It's after lunch and before the coffee break, so if I hear some snoring, I'll blame the food and not my slides. Just kidding. Okay. We'll get started here. Thank you, AZ, for the introduction. I don't need to go through all of this again. This is just a little bit about my background. So I started off in the industry when I was about 5. Just kidding. No, actually, I was 18 years old. I took a year off I didn't want to go to college, actually, and despite the pressure of my dad, I decided to join AmeriCorps for a year. So I worked for a Habitat for Humanity down in Louisiana, actually, not far from here, Houma, Thibodaux, right in between, Gray, Louisiana. And I was hired to be a construction crew leader, but I knew absolutely nothing about construction. So luckily, I had some long-term volunteers that were on site that took me under their wing, and I obviously was curious, interested, and over that course of the year, I learned how to build a house, framing, roofing, siding, windows, doors, trim work, carpenter, all that fun stuff. And that got me really curious about how houses are built and how we could build them better, more efficiently, more sustainably, better for the occupants. So again, my dad wanted me to go to college, and so he did some research for me and found the building science program at the University of Minnesota. And I thought, oh, that sounds perfect. So I went there, did that, and then I kind of just, one thing led to another. I worked in weatherization for a couple years. I did a lot of blower door testing, infrared imaging, weatherization kind of things. And then I worked for a home performance insulation company for another 5 years. I did a lot of diagnostic testing on houses, trying to figure out what was causing different problems, comfort issues, indoor air quality issues, ice dams, things like that. Being from a north climate, we have a lot of those issues. And then Ruben Saltzman at Structure Tech scooped me up and said, hey, have you ever thought about being a home inspector? And I was looking for something different, a new challenge, and I thought, well, I never thought about being a home inspector, but why not? Sure. So I became a home inspector, and I did that for about 7 years up in the Twin Cities. And now I have my own consulting business. It's called Your House Coach, and I work with homeowners primarily, but I also work with anybody that deals with houses. Houses have issues, just like people do. Human bodies, we go to doctors when there's something wrong. They help diagnose what's happening, send us to different specialists, referrals. That's kind of how I look at what I do. I assess the house as a system, and I work with people to try and figure out the best path forward to resolving those issues. So, okay, let's get into it here. This is the agenda. I've got a lot of slides to get through today, and I was told that I need to have you done early to get to the next session. So I'm going to be flying through these, so bear with me. We're going to talk about the house as a system, holistic thinking. A lot of times in our industry, all the trades are very segregated. They look at their one specific area, and they know that well. But who understands all of the systems and how all the systems work or don't work together? And I think home inspectors are in a very unique position where we know a lot about a lot of the different systems. So I want to kind of invite you guys to take it one step further today and to add onto your business kind of this perspective, this holistic perspective of looking at a house and understanding how all these different parts and pieces fit together. And when you change one little thing, you can impact another. We're going to touch on, of course, building science, the basics of that. Other things that matter to clients too, indoor air quality, durability, efficiency, comfort. And of course, we're going to dive into some real-world case studies too and apply these principles to that. So, what is building science? Let's get started with that. It explains how heat, air, and moisture move through a structure and how that impacts durability, efficiency, comfort, and health. To create high-performance buildings, we must intentionally control these forces to prevent problems and ensure long-term success. That's a quote from Joe Stebrick. And I apologize, this, this version of the presentation is not the version I thought it was going to be. I have a little image of Joe Stebrick that's supposed to pop up. For those of you that don't know who he is, he's a very well-known building scientist in the industry. So I will reference his work and his quotes kind of throughout this presentation. Why systems thinking matters. As I said before, homes are dynamic systems. Everything affects everything else. And you can make one small change in an area, and it can have a ripple effect throughout the house. So we're gonna kind of look at examples of that throughout this presentation. And by thinking about the house as a system, not only are you providing a better service to your client, better education on what they're getting, but you're also protecting yourself too, liability-wise, diagnosing and seeing these sometimes tougher things that aren't super obvious. And also you're just, by thinking, differently holistically too, it gives you a competitive advantage, which I know Mark would be proud of me for using that today in the presentation. So, okay. This is a very different version of this presentation. So bear with me, I don't know what I'm gonna see next. Okay, so this is just a little visual of all the different parts and pieces that kind of come into the house as a system. We've got the occupants that play a big role. We've got the building, the structure itself, the environment, and the mechanical systems. Okay, so heat, air, and moisture are always going to be moving through the house, through the building envelope. And we can have failures if we don't control these airflows and this moisture. So today, our occupants demand a lot more from inspectors. They expect more out of our houses. Okay, so I'm gonna need your help on this one, Tom. Some failures are obvious, like this. This is actually a video Ruben Saltzman took on a new construction. It doesn't take a rocket scientist to figure out that this house is going to have major water intrusion issues, correct? And is this a design fault? Is this a construction fault? Who knows? But we're gonna have problems with this. Some are obvious, like I said, and some are not so obvious. Some are like this, right? So I want to give you some skills. Okay, this is not the right presentation. I apologize about this. Yeah, let's swap it. 1 second, you guys. Okay, expanding your role as a home inspector, just from going from a box checker, someone that goes through and looks for these specific defects, this is wrong, this is wrong, this is wrong, helping you guys identify these specific kind of symptoms in a house that could mean a larger picture. The house could be having comfort issues, durability issues, indoor air quality issues, and all those things matter to clients. They care about that. I know it's beyond the SOP, but to set yourself apart, to deliver a good product to your clients, to build trust, it's nice if you can take that step back, put all those pieces together, and start recognizing some of these bigger patterns that are happening within a house. A lot of people think that if a house is built to code, then it's fine. Right? It's not going to have any problems. So it's built to code. Code is just the minimum standard. So systems thinking goes beyond just that checklist compliance. This is an example of a new construction house, middle of winter. There's water dripping down the soffit, down the exterior walls, coming out through light fixtures, coming out through exterior windows, dripping all the way down. So house was brand new construction. It's not a roof leak. Something's going on. So just because it's built to code does not mean it's high performance. Before we dig into the building science, I think in order to understand how a house works or doesn't work, we need to understand how it's built, the materials that are used. There's a big difference between old houses, quote unquote, and new houses today. And so I just want to touch on that with you guys. In general, older houses were a lot more leaky. There's a lot of air exchange happening in them. Airflow was uncontrolled. Didn't have much insulation, so a lot of times they'd be drafty, uncomfortable, expensive to heat and cool, right? But because of all those things, they were very durable. Whereas new houses today, in general, they're a lot more airtight, they're better insulated, but because of that, they're a lot more fragile. We have to be even more careful about those the pathways for air and moisture. They're more complex. So what caused a lot of these changes? Okay, quick summary. We've had an increased amount of insulation we're using in houses today. We have reduced permeability of materials that we're using as well, like vapor barriers, vapor retarders. Houses 100 years didn't have that. 100 years ago didn't have that. We've got more moisture-sensitive materials too. So this picture right here on the left, It's a cross-cut section of an old-growth tree, and you can see that darker ring that takes up the majority of that cross-section is heartwood, and heartwood is naturally more decay-resistant. It can handle pests and water. The lighter ring around it is sapwood, and it's not as durable. So the difference is trees that were grown 100 years ago were grown slowly over time. They had a lot more heartwood in them. Trees that we use today for construction materials are grown on tree farms really fast. They're cut down. You can see the image in the middle, examples of that. They're much smaller, and they have a lot less heartwood in them. The majority of them is sapwood. And then we take that sapwood and we grind it down to pulp and we glue it and press it together. So how does that handle getting wet? Not very well, right? So there's just a big difference in the materials between old houses and new houses. Also, houses are a lot more airtight. Again, we're trying to make them more energy efficient. And we've got complex air leakage. So here's an example, old house. On the left, we've got wood wall sheathing. That's actual dimensional lumber from old growth trees. And a lot of times, there's very minimal insulation in the walls, and you might have lath and plaster on the inside. This is common for upper Midwest construction. We might see something different in your neck of the woods. How many people here are from, would you say, a predominantly like heating climate, cold climate? Raise your hand. Okay, quite a few. How about from a southern climate or a hot climate? It's okay. I'd say it's about half and half. All right. So where I lived, this is pretty common. You'd see in old houses, it would just be the wood wall sheathing. We'd have a little bit of insulation, if any, and then the lath and plaster on the inside. So you can imagine, if there's a little bit of water that leaks in around the window, that wood, it holds up pretty good, right? There's a lot of heat loss and air movement going through that wall. It's going to dry it out, and the wood can get wet and stay wet for a while before it starts rotting, okay? Versus new construction today. We've got this wood material that when water starts leaking around a window, that material gets wet and it stays wet. It doesn't dry. We don't have the amount of heat loss happening through the wall because we've got walls full of insulation. And on top of that, we usually have vapor barriers that prevent drying as well. So now that moisture gets in there and it stays in there, and we can have catastrophic failures just from a tiny little leak around a window. So old house will handle it very differently than a new house today. And I think it's important to understand kind of what you're looking at when you're inspecting. What are we dealing with here? And then everything in between. You take an old house and you make it new and you, quote, improve it. We need to be thinking about air and moisture and heat and how it moves through the building structure to try and avoid these problems. So in the industry, building science, we say build tight, ventilate right. A lot of people say, I hear this all the time. How many of you have heard this? Houses need to breathe. Yeah. Okay, well, that's a myth. People need to breathe, but houses need fresh air, and they need to be able to dry out. It's important to build tight so that we can control how the heat and the air and the moisture move through the building structure, and we don't have problems with air leakage and moisture. But we also need to make sure that if we're going to build a house really tight, that we provide some sort of ventilation strategy as well to maintain a healthy indoor air quality. And like I said before, something can get wet as long as it can dry out, so that's really important as well. This house looks nice, built in 2003. This is Indiana, so it's a heating and cooling state. Looks nice. This homeowner moved in. They had a inspection that they had done, and then also the seller had an inspection that I did. So this house had 2 inspections. Everything looks nice, but shortly after moving in, noticed a soft spot in the wall. So we got a little curious, made a hole, and one thing led to another. Yeah, so building science can help us as inspectors think about what's going on behind the scenes, not just going through the house and checking boxes, but, okay, what caused this and why is it there? So we can help identify these big problems and protect our clients from issues that can cost them tens of thousands of dollars, right? And protect you, too. So how did that moisture get in there? How did that mold form? Let's get into the fundamentals of understanding building science here. Okay, 3 key players. It's all about heat, air, and moisture. My building science professor at the U of M used to call it the ham sandwich. Okay, so I'm just going to touch on basic principles here of thermodynamics, so bear with me. Energy is conserved. It can't be created or destroyed. And also, this is the dumbed-down version, heat flows from hot to cold. To be a building scientist, that's all you got to know. That's it. Wish I could give you guys a certification after this class, but and then reversing that heat from moving from more to less or hot to cold, you have to throw more energy at it. So it would require something like AC or heat pump to do that. So the takeaway, okay, heat is always moving, and it's our job to try and slow it down, and we control that with insulation, air sealing, and HVAC. That's how we control it. So it's the same no matter if you're in a cold climate or a hot climate. Heat is always going to go from more to less, hot to cold, and it's our job to try and reduce that so that the house is more energy efficient, more comfortable, and of course, control those airflows so it's more durable as well. So let's dive into heat first. Heat, again, moves from more to less, and change in temperature is what drives that heat transfer. So the greater the temperature difference, the more heat transfer you'll have. And there's 3 modes. I'm sure you guys have all heard of this, so this is hopefully just a quick review. Heat can move through conduction, which is heat transfer through solids like walls, roofs, floors. It can move through convection, which is through a fluid like air leakage. And it can also move through radiation, which happens in waves. So like solar radiation, sun beating down on a roof, or sun coming in through a window. So an example of conduction, heat loss, here's an IR picture of a wall that's missing some insulation. So we're gonna have lots of heat loss through that wall, and you can see the cold spots where the insulation has fallen down or is missing. Now, we're gonna have a lot more heat loss through the framing than through the insulation. And depending on the design of the house and what climate you're in, this could actually create problems, even though you've got closed-cell spray foam in between these roof rafters. We've got a roof deck right on the other side of that, and we're gonna have sheetrock on the inside, and so we're gonna have a lot of conductive heat loss moving through that sheetrock, through the rafters, to the roof deck, which melts snow potentially on the roof deck. And when you melt snow, you could potentially create an ice dam, which is that snow melts, and then that liquid water refreezes at the eave where it's cold, and then you get a literal buildup of water behind that ice dam, and that can create water intrusion. So you'll get clients that will spend tens of thousands of dollars installing the best insulation out there that they can with the highest R value per inch, thinking that that's going to solve their ice dam problems. But whoops, we didn't think about thermal bridging and heat loss through transfer through the framing, right? And so we're still going to have heat loss, and we can still have performance problems with the house, even though we upgraded to a better type of insulation. Here's an example, a house that has slant areas, and you can see the rafters are much colder than the spaces in between that are filled with insulation. So we've got heat loss moving through that. Ghosting, how many of you have seen this before? Okay, where we've got heat loss moving through those studs again, and a lot of times if we've got a lot of humidity in the house and we've got soot or ash or someone smokes, all of that can stick to the condensation on the walls. Then it can literally show you where all the framing is. Okay, looking at convection, an example of that. How many of you have heard of the term stack effect before? Okay, yes, I like it. All right, half the room I'd say. What is stack effect? Okay, so cold air is more dense, so it will sink, it will fall. And as it falls, it will displace the warm air and push it up. So we have this kind of natural effect where the warm air is more buoyant, it will rise, the cold air sinks. We can get convective looping that happens in a house, but a lot of times houses have air leakage at the lid. It can be anything like electrical penetration, plumbing penetration going through the ceiling. That warm, moist air will rise and find its way through those little penetrations and move up and out of the house. And a house is not a vacuum. So if we're losing air out of the lid, more air is going to be pulled in to replace it, lower in the house. So we end up with this positive pressure at the ceiling and a negative pressure at the lowest point in the house that's actually pulling air in. So if you have a house that's really leaky, you'll have a bigger temperature gradient between the upstairs and the downstairs. It'll feel really cold in the basement in the winter. It'll feel really hot upstairs because of that heat rising. Okay, so here's another graphic that shows from the Energy Conservatory. They're a company out of the Twin Cities that shows stack effect in a taller building. So the taller the building, the greater the stack effect that you can have. And on the left, it shows in the wintertime, you'll have warm air rising, and it will leak up and out of the lid through just different bypasses around windows, electrical penetrations. It creates a positive pressure at the top. And then, again, you're pulling in that cold air to replace it lower in the building, creates a negative pressure. And then somewhere in the middle, it's going to be zero pressure change. It's called the neutral pressure plane. You'll have no air leakage. Now, you reverse that for summer conditions. So hot, humid climates is the exact opposite. You've got hot outdoor air. Heat wants to go from more to less, and you're cooling. And so all that cool air is sinking down to the bottom, and it's being pushed out lower in the building. And then as that air is leaving, more hot, humid air gets pulled in to replace it higher in the structure. So it's just flip reverse of that, of the cold climate. Negative pressure at the top, positive pressure at the bottom. This was an inspection I did on a condo and a high-rise, and obviously it was winter. I went to go test the exterior outlet, and I couldn't get the lid open. It's because it was frozen shut. So this is a perfect example of convection, right? We've got warm, humid air in this building that's leaking up through the exterior wall, through the electrical penetrations, trying to push its way up and out, and it hits the metal cover for the electrical outlet and freezes and condenses. So this is just an example of how that moisture and how that airflow is moving through these buildings. Okay, and then radiation, the last piece here, again, you can have solar heat gain through a roof or through windows. I was doing some habitat builds in Florida, and one thing that was different I noticed is that the roof decking actually has like a built-in radiant barrier to the backside of it, the OSB, to help reflect out that sunlight so that you don't get as much solar heat gain in your attic. Kind of interesting, I thought. We don't have that in Minnesota. Yeah, question. Mm-hmm.
Going back to we had the thermal bridging.
Yeah.
You just showed.
Yeah.
So down in Florida, we had that transfer of heat, and you have the reflection of heat loss. Right?
Yeah.
So would radiant panels or radiant sheathing help deflect that as far as air loss?
Well, so we're talking about solar, like radiation heat, which is different than heat being moved through air. And so you've got kind of a bunch of different things happening. And so having a radiant barrier is definitely a good thing if you've got the sun beating down, making that attic hotter. That will help reflect some of the heat. I don't know if I answered your question.
Yeah, that example that you showed where you showed the trusses, that was when you get your escape of air, right? And when you had that loss and you have damage potentially on the wood, would radiant barrier there help support that thermal bridging that you mentioned earlier?
So thermal bridging is not, it doesn't have to do with air. It has to do with heat transfer through solids. So yeah, so conductive heat loss. And so yeah, you could have transfer of heat through the truss from the roof deck through conduction, making that space warmer. And that's why we have thermal breaks, or why we would have insulation to help slow down that heat transfer through the roof trusses. Yeah. Yeah, question, Jeff. Yes. Yeah. Yeah. Yes, good point. Good point. Okay. We've got some building science experts in the class too. Please direct your questions to Jeff afterwards if you had it. Okay. Moving on. So that was heat. Let's touch on how air moves, okay? Just the basic principles. In order to have airflow, you need two things. This is very basic. You need a hole and you need a pressure difference. That's it. If you don't have a hole or you don't have a pressure difference, there's not going to be any airflow. Yes. Good question. If it's like a long wall, I guess you'd need like a tunnel. So how do you define that? Is that one hole or is that two? But just for that air to move from one place, point A to point B, is what you need. You need a hole. So I'll show you some examples of that too. So the rate of airflow is the function of the hole size and the pressure difference. So the bigger the hole, the bigger the pressure difference, the more air exchange you're going to have, okay? So what causes these pressure changes? It can be several different things. It could be wind hitting the building that can create a pressure difference. and drive airflow changes. It could be stack effect, what we just talked about, changes in temperature. It could also be mechanical ventilation inside the house that creates different pressures, that causes airflow. Okay, so what's interesting is people say, again, this theory that houses need to breathe. Old houses were leaky. Well, that was a good thing. Okay, well, I'll counter that. If you have a very leaky house, and let's just say a really hot, humid climate, okay, you're gonna have the most air exchange happening when it's really hot outside. So you're pulling in that hot, humid air. Same thing in a cold climate. The colder it is, the greater the temperature difference, the greater the pressure difference, the greater the air exchange. And so in a really cold climate, you're gonna be pulling in cold air in the wintertime, which will help dry your house out, but it's also gonna cost you a lot of money to heat. Right? So we want to try and build a tight house and control these airflows so that it's energy efficient and comfortable. But we also need to be even more cautious then, if we're building it airtight, that we do it well so we don't have these channels that can carry air and moisture and create problems. Now here's a great picture, I think, that depicts typical air leakage locations in a house, in a standard house. So you've got all sorts of places air can leak in and air can leak out. And this is assuming it's, it's cold outside, warm inside. We've got the warm air rising. If you've got ductwork in the attic, recessed can lights, drop soffits, all those are potential places for air to leak out. Okay, last piece here, moisture. Moisture, obviously, everyone's worst nightmare. It's house's worst enemy. It creates mold, moisture, durability issues, health risks. So to manage moisture is to manage risk, okay? Now moisture always goes from more to less, from wet to dry, and from warm to cold. It's the basic principles here. This is a psychrometric chart. It looks intimidating, but this is just a graphical representation of thermodynamics and how it works. So let me explain this. On the bottom x-axis here, we have temperature, dry bulb temperature. So let's just say we've got a house that's 70 degrees inside. Okay, so we circle 70. We'll draw that line straight up so we can see. Then these curved lines represent relative humidity. So let's just say we've got a house that's 50% relative humidity. We follow that curve down to where it intersects with our dry bulb temperature, and then we go straight across, and where that line intersects with, let's see if I can use a pointer, with this curve right here, this is the wet bulb saturation temperature. That's another word for condensation. So that is the point where we will get condensation. That's the temperature. Okay, so you can see the more humidity we have in the house, the higher that dew point is going to be, right? And that's when we have problems, is when moisture condenses in houses. So what I tell people, if they've got condensation, mold issues, okay, well, either we can increase the temperature to increase the dew point, or we can decrease the humidity to reduce the dew point. Does that make sense? And usually the best thing is to increase the temperature and decrease the humidity. You're less likely to have condensation that way. Now, if you really want to impress your clients, you can carry around a psychrometric chart like this, but I prefer using like a little app on my phone, which, you can plug in whatever the temperature is, whatever the humidity is, and you can see what the dew point temperature is, and there you go. And you can show a client, well, that's why you're having condensation in the back corner of your closet on the exterior wall, because it's blocked off from heat and airflow, and it's really cold, and so when that humidity touches it, it condenses, and that's why we've got mold there. Question? Yes, both. They go hand in hand. Yeah. Yep. Good point. Okay. So, how it moves. How does moisture move? Several different ways. Bulk water, which is like rainwater coming in, snow. We can have capillary action. We can have air that transports moisture, which we've already touched on, and vapor diffusion. Bulk water is usually the biggest problem. It creates the most expensive issues the fastest if we have water leaking into the building envelope somewhere. So that is what we want to try and prevent and stop first and foremost. Exterior water management in this case is critical. That's flashing details, roofing, siding, windows, all of that matters. And again, if it's a newer construction house, it matters that much more. All those details are done correctly. So here's an example. This is an older house, 100-year-old house in Minneapolis. It was missing the kick-out flashing for a very long time. They were doing a big remodel in this house, so I was able to go inside, and you can actually see, after years and years of that water running down inside the wall, it has rotted out the wall sheathing. So now we got structural stucco. So again, bulk water is usually can create the most expensive problems the fastest. Here's another example, newer house, thinking about where all the water goes. It's draining down here. We were missing kick-out flashing here. And we've got, a brick veneer, which is going to soak up moisture too. So first thought is let's go inside and make sure we don't have any water intrusion. Had an IR camera. And IR cameras, if you take Bill Fabian's class today, he'll probably talk about this. Actually, sorry, I think he's teaching the same time I am. So here we go. Here's our IR lesson for the day. It doesn't actually see moisture. It just sees temperature difference. So this area is cold, but it's also right in alignment with that area on the exterior where we've got all that water draining down into the wall. So pull back the carpet. Looks fine. Whoop. Okay, no, it's not okay. We'll just put the carpet right back and everything's fine, right? No. Okay, same thing. Where does the water go? We've got all this water coming off the roof. We don't have any gutters. It's hitting the deck, splashing back against the house. We don't have proper flashing details over the ledger board. So spidey sense going off, run the moisture meter. Luckily it's, vinyl so we can peel it up, do a quick scan. It's wet. Luckily the basement's unfinished, although we've got nicely placed ductwork that blocks it. We can climb up behind there and look, sure enough. We've got some major water intrusion issues. And all these are, unless you go digging for it, you don't necessarily see it, but you just have to take a step back sometimes and look at the big picture, right? So that's bulk water, okay? We can also have capillary action. What is that? Okay, when you stick like a paper towel in a little bit of water, how it soaks it up? Okay, that's capillary action. So concrete, if you've got a basement below grade or even a slab on grade, concrete that's in contact with wet soil will soak that moisture up. When that moisture moves through the concrete and dries to the inside, because remember, moisture goes from more to less, wet to dry, when it evaporates, it leaves behind the salts. And we call that efflorescence. I've got some pictures of that coming up. And how do we stop capillary action? Well, we try and use capillary breaks. We try to improve exterior water management the best we can, gutters, downspouts, grading, all of that. And also, we try and provide drying to whatever that moisture is moving through instead of trapping that moisture. So here's some examples of efflorescence. You can see all that kind of fuzzy stuff on the inside of concrete. These are all basements in my neck of the woods. If a house is built before they did waterproofing on the exterior, which is anything prior to the 2000s, we will have efflorescence happening, most likely. Even in sandy soil, you can still have some moisture that wants to come through. Capillary action through masonry stone veneer, that's not installed properly. What is this missing here? Yeah, weep holes, clearance to grade to the dirt, right? So what happens when you take basically a sponge and bury it in dirt? Well, it soaks up water, right? And same thing with stucco. Stucco behaves the same way. It can be sucked up through stucco. Now, what's interesting is this house, the grading had just kind of been piled up over the years, and now the wood framing is below the dirt level. And this was a client who bought this house at a time where inspections were being waived. They moved in, first-time home buyers, and shortly after found out that they were missing their rim joist and a lot of their wood was rotted. That moisture moved right through the soil, through the stucco, wanted to go from more to less, dry to the inside, and now they're having to redo all of the framing. This is a house in Florida, actually. This was recently. Friends of mine that had just installed a nice vinyl flooring that was like guaranteed for a lifetime, whatever that means. And we're told that it was a good product and it could handle moisture. So they put that down on their concrete slab, and 2 years later, it's all warped and it's coming up. And you can see this house is not flooded. This is all the moisture that's wicking up through the concrete and then getting trapped behind this material that does not breathe. It's a vapor barrier, okay? Yeah. Well, yeah, I mean, you could put a vapor barrier underneath a vapor barrier. It's just going to change where the moisture gets trapped, right? Good question. So, okay, moving on. Air can also move moisture as well, air transport. So, moisture from the house can leak up into an attic, like we talked about, through convection and air transfer. We can have humid air from a crawl space that gets pulled into a house as well through air leakage. That's why, of course, it's important to air seal our house and make sure build tight, ventilate right. Here's an example, worst case scenario, cold climate, very unforgiving. This was new construction, lots of moisture in the building materials in general, but a ton of air leakage happening, and all that moisture is leaking up into the attic, condensing on the cold roof deck, and freezing. And if that goes on over and over and over again, repeatedly, it can look like this. This is not a roof ventilation issue. This is an air leakage issue. Vapor diffusion, last way that air or moisture can move. Vapor can move through materials like drywall. It's vapor permeable. That's why we use things like poly vapor barriers or some type of vapor barrier or vapor retarder. And just depending on where you live, the climate, what the code says, will depend on where you put that vapor barrier. So in a cold climate like Minnesota, we're required to put that on the warm side of the wall on the inside because predominantly that heat wants to go from more to less, hot to cold. We're heating our house, so we want to keep that vapor inside. We don't want it getting into the wall cavity and condensing. Flip that for a hot, humid climate. Yeah, question. Yes, you brought up a good point. I'll try and repeat that. So he said we'll always have humid air in the attic. And yes, depending on the climate zone too, you can have warm humid air from the house leaking up into the attic, and if it's a cold climate, condensing, creating mold, moisture problems. We want to try and air seal that lid between the conditioned living space and the attic so it can't leak up and get up into the attic. Yes, but then we can also have humid air coming in if you're in a humid climate up through soffits, you're right, and we can't control that, and so that's why we need good ventilation as well in an attic primarily. Yes, you want to have good airflow. Good point. So this is just a quick picture. This actually comes from Building Science Core. This is Joe Stebrick's foundation, but it shows basically if you've got a brick exterior wall and it's raining outside, that brick soaks up the moisture like a sponge, holds on to it. If it's 80 degrees outside and sunny, and it's 75 inside and you're cooling, okay, that sun comes out, beats down on the wall, heats up that wall cavity. Which way is the vapor going to go? Remember, moisture goes from more to less, from wet to dry. Okay, so if it's 100 degrees inside that wall cavity, it's really hot here. It's 75 inside, it's 80 outside. And the humidity, you can see it's 100% inside the wall cavity. It's 60% inside, 75% out. So we actually have vapor drive going both directions. That wall wants to dry both directions. So that's why it's very important to have some sort of airspace behind brick or stone veneer to allow for venting so that that moisture can go somewhere. So it's not being driven inward. And if you're in a climate, like a cold climate like Minnesota, where we've got a vapor barrier on the interior wall, that moisture, that vapor drive can actually push through the exterior weather resistive barrier, because that's not a vapor barrier, right? It breathes. Vapor can move through that, through the wall sheathing, through insulation, unless it's like closed cell spray foam, which is a vapor barrier. But if you got fiberglass or cellulose or rock wool, the moisture will move through that insulation, and then what happens when it touches the back of a cold, air-conditioned vapor barrier? It's going to condense, and we get moisture problems, right? So it's important to have that airspace. Here's an example of a house in Minnesota. We've got stone veneer. What happens when it rains and it gets wet? Sun comes out. Even though it's a cold climate, that vapor drive is pushing inward. We've got nice air-conditioned cool inside. What's it look like on the inside? Can you guys see all these little black spots everywhere? Okay, well, that's mold, right? Yeah, I'll say it, it's mold. It's mold. So that's a phenomenon that happens. The worst thing you can do is put a vapor barrier on the warm side of a wall when it's hot and humid outside, because that vapor drive is going to be pushing inward. So like in Florida, we don't want to see, typically, a vapor barrier on the warm side of the wall. And to quote Joe Seabrick again, he said it better than I do. Top 10 dumb things to do in the South. Vinyl wallpaper. This is a vapor barrier on the wrong side of the wall. It should be put on the outside of buildings, not the inside in the South, right? So just to put it into perspective, we've got moisture that can move through air transport, but also through vapor, okay? And we talked about both of them, but I just want to show you, this was another test that was done by Building Science Corps where they had a wall cavity and they tested how much moisture actually moved through that wall, through a 4x8 sheet of sheetrock during a heating season. And they had 70 degrees inside, 40% relative humidity, and they measured how much water got in the wall just through vapor diffusion through that sheetrock. There was no vapor barrier behind it. They got a third quart of water. Then they also did the test with a 1 by 1 inch hole in that sheetrock, and they got 30 quarts of water. That's a lot of water, right? Again, so if we want to try and reduce the amount of moisture getting into these wall assemblies, getting into the attic spaces, getting in crawl spaces, we need to really make sure that we're air sealing our buildings well. Just one tiny little hole can transport a lot of moisture. And the more humidity you have, the worse the problem. And the tighter you build, the more humidity you can have that stays in the house if people are showering, cooking, breathing, all of that. That's why ventilation is so important. Going back to this house, new construction, passed all the codes, passed all the city inspections. We had this water that was dripping down the exterior wall. What's causing this? It's not a roof leak. It's not an ice dam. What was that? It's sweating. Okay, yeah, you got an idea? Bathroom vent, all good theories. Okay, let's see what's going on here. Again, we've got the staining that's happening. Here's what the inside looks like. Okay, what do we have in the ceiling? Can lights, penetrations, right? Over a bathroom, high moisture location, right? More can lights. Water staining. More can lights. This builder really liked their can lights. Okay, here's what the attic looks like. Oh, good, they're being proactive. Okay, this is a scissor truss, so there's a little bit of space at the peak. You could kind of walk. It was really tough to get down to the eaves, but we know we've got can lights at the eaves, right over top of showers, right? I wonder if they're air sealed. Okay, well, another question a lot of people have, well, is there proper venting, right? Everyone always thinks the moisture problem in the attic is because of the venting. Well, we've got vent chutes, we've got soffits, I see airspace, we've got a continuous ridge vent that's installed properly. Check, check, check. Well, that's better than average. What about bath fans? Are they disconnected? Are they blowing hot, humid air into the attic? Well, all the bath fans are accounted for. They're all venting up and out properly. Okay, so what about these penetrations in the ceiling? Let's dig some insulation back. Yes, not sealed. So we've got a bath fan. You can see it's hot in the house, cold in the attic. We've got all this heat loss happening around. Bath fan, number one. Yep. Plumbing vents might look small, but remember that 1 inch by 1 inch hole from that study? How much moisture can move through that? Okay, so take those can lights times 100, and you can really get a lot of moisture into that attic. So we've got all that warm, humid air pushing up and out. It's cold outside, leaking through all these penetrations. This house passed all the city inspections. It was built to code. It's pretty airtight, 3 air changes per hour or less, but because of the building science, what's happening, it did not perform well, right? We've got problems. Oh, and to make it worse, this builder put in, which you think would be an upgrade, closed-cell spray foam in the exterior walls. And he was really proud of that. Closed-cell spray foam doesn't really absorb or hold moisture that well, right? So all this water was getting up into the attic, condensing on the underside of the roof deck, forming a layer of frost when it was really cold. And then as soon as the sun comes out, warms up the roof deck, that frost melts, drips down, hits the exterior wall, and runs all the way down the exterior wall because nothing can absorb it. So it's coming out at the first opening it hits. Yep, it's crying. Okay. This is a house, story-and-a-half house, cold climate as well. You can see now, frost is Mother Nature's IR camera. So look at these melt spots we have. Isn't that interesting? This house has been spray foamed. The whole thing has been spray foamed and hot roofed. but we've got these pathways that are still getting warm. So we did a blower door test. You can see, look at all these cold spots happening. Discrepancies where little spaces didn't get sealed. And sometimes it's as simple as you need to caulk between the rafters where the wood meets, or the rafter touches the top plate of the wall, because air can move through that. And just imagine, now we've got all that warm, moist air that's leaking up behind the spray foam, in between the spray foam and the roof deck, and it carries moisture with it. What's going to happen to the roof deck? It might start looking like this, right? Here's another cathedral ceiling. We've got air leakage happening here, that warm, moist air condensing on the underside of the roof deck. Over the years, we can start to rot out the roof deck. Now, that's all dark staining from moisture. Here's another modern building, low-slope roof. This is a recent client of mine. They had a new roof put on. They decided to upgrade to spray foam. Now, I don't have anything against spray foam, but if it's not done perfectly, you can end up with pathways of air that can move through these little leaks and gaps, and what moves with the air? Inevitably moisture, and we can get problems in a climate where it gets really cold or it gets really hot. We've got air conditioning, ductwork. When that moisture hits a cold surface, it can condense and create problems. And so they were having all sorts of moisture problems after they did this spray foam, this hot roof. They've got a tongue and groove ceiling. And so what was interesting is the spray foamers came out and they sprayed foam to the back. They put a cardboard backer down because they didn't want the spray foam coming out between the tongue and groove wood. And the clients really loved their tongue and groove. So they kept that. That was the priority. But because they put down a cardboard backer, a lot of times that spray foam is not going to adhere to that ceiling. So now we can have little pathways between the tongue and groove and the cardboard where it doesn't adhere. And now we've got issues. And this is in the summertime. We've got all this condensation happening. We've got really hot, humid conditions outside, air conditioning inside. We're pulling in that hot, humid air. It's moving through these little pathways, and it's hitting cold surfaces, and it's condensing. So what did they end up doing? Ripping off their brand new roof deck and looking at the foam. And actually, I think there's more problems than just the cardboard. That foam is pulling away from the rafters too. So this is a bigger issue. This foam was probably not mixed right and definitely not installed right. Okay, so moving on from heat, air, and moisture. Another thing that's really important to clients and to the success of a building is just, in general, air quality. So many people come to me, their number one concern is health. They're feeling like their house is not healthy or it's making them sick. And as home inspectors, I mean, that's beyond our scope, right? But there's a lot of things we can look for and look at in houses that can be indicators of a potential air quality problem that I think we should educate our clients about. So I'm not going to go through all these in detail because we don't have that much time. But we can have biological contaminants that create issues for people: mold, dust, pollen, bacteria, all of that. Of course, mold is just a symptom of a moisture problem. So where is that moisture coming from? Is it coming from bulk water? Is it coming from air transport? Is it vapor diffusion, capillary action? Where is it coming from? A lot of times it's not just one source, it's multiple things happening in a house that's contributing to a moisture mold problem. Okay, humidity, excess humidity, and again, especially as we're building houses that are more airtight, more insulated, humidity is becoming a bigger and bigger issue in a lot of homes. And so looking at some sort of kind of dehumidification system is kind of going to be the next front, I think. So here's an example of a house right away. Woo, we've got water streaking down the windows. We've got way too much humidity in this house. This is a symptom of a much bigger problem. Right? When we see condensation like that, we've got a humidity issue. And a lot of times, I don't know if you see a lot of these in the South, probably not, but in the North, people love their whole house humidifiers that basically just pump moisture into the ductwork, which then gets distributed throughout the house. And as you can imagine, pumping moisture into your house, especially if it's a very leaky house, which usually the leakiest houses are the driest houses in the winter, right? Greatest air exchange. That moisture is going everywhere you don't want it to go, into the walls, into the attic, and it creates moisture problems. Yeah. Yes, I said, did you say humidifier? Yes. We're crazy. We put humidifiers in our house. Yes, yes, very smart. You guys are smarter than us. In cold climates, because our houses are leaky and drafty, they get very dry, and people complain about, dry conditions. It sucks when you go to turn on the light and you get shocked every time, so they crank these things up without realizing that all that moisture is going somewhere, right? Yeah, big problems. So I'm not a fan of those, especially if you've got a leaky house. And if you don't have a leaky house, you probably don't need one. Other things that impact indoor air quality, chemical pollutants. And I'm seeing more and more of this too, especially as sensors are coming out. Homeowners are buying these things, they're tracking it, they're getting more concerned. VOCs, formaldehyde, radon. We also have combustion byproducts that can impact indoor air quality, carbon monoxide, fireplaces, attached garages that are connected to the house, furnaces, boilers, stoves, all of those things. Fine particulates from cooking, especially with all the wildfires that we've had recently. This creates a lot of health concerns as well, fine particulates, smoke, tobacco. We can also have HVAC issues that contribute to air quality problems. Inadequate ventilation, poor HVAC maintenance. We could have unbalanced air pressures that's actually pulling air in from places like tuck under garages or from the exterior. We can even have backdrafting combustion appliances like natural draft water heaters. If they're not drafting properly, they're dumping carbon monoxide and moisture into your house. We're going to skip that video. How many of you know what a backdrafting natural draft gas water heater is? Raise your hand. Okay, if you've got an older style natural draft water heater that has this gap at the top and it vents up through a metal flue, this type of appliance is just relying on that warm air from combustion to vent up and out through the house, and it's very susceptible to pressure changes. And so lots of different things could potentially cause that to not draft properly. And then we can have carbon monoxide and other gases coming back into the house. I'm not going to get into all the reasons why it could be backdrafting. There's a lot. It could be, clogged vent or, improper slope. A lot of times, though, what causes it? People replace an older style furnace or boiler with a high efficiency one that now vents with PVC pipes out through the roof or through the rim joist. Now that water heater is venting all by itself up the chimney. It wasn't sized for that, so it can struggle to vent and establish a proper draft. So we call that an orphaned water heater. So more and more we see in my market where we've got these older style water heaters, people upgrade to a new high efficiency furnace, they leave the water heater, and now the water heater can't draft properly. What makes it even worse is when people start air sealing their attics, and then they start putting in new windows, and they start doing spray foam, and then they maybe add some bath fans that create a negative pressure and suck the air out of the house. All these things are making the house more airtight and creating a negative pressure. It makes it harder for this type of appliance to draft properly. Okay, so we're thinking about these things as we're walking through the house. Wow, this house has been air sealed. It's gotten pretty tight. They've replaced the furnace. Oh, we still have a natural draft water heater. How's this thing drafting? Is it drafting okay, or is it backdrafting? Because if it's backdrafting, that could create really bad, could have really bad consequences with it. So are you checking for that? What are you saying to your client? I'm going to skip through this. I just want you guys to be aware of these potential issues. We can talk about backdrafting all day long. We could have a whole class on it. Yeah, question? Yeah, when there's corrosion around the outside, usually that's an indication that we have. Oh, on the vent itself. Yeah, sometimes that can be from condensation, and then it started to corrode it. Yeah, so keep an eye out for that too. We can have other things that create indoor air issues too, external pollutants like I mentioned before. Again, it's important to build tight. And even occupants play a role with that too, with indoor air quality, right? This was someone who liked to smoke when they were taking a shower. And we've got all that soot sticking to the cold areas of the roof. You can see where the trusses sit right here. Okay, so for indoor air quality, what's our strategy for improving this? All of these things, for tackling these challenges. Number one, try and remove the source, right? Number two, after you've done your best to remove the source, provide some sort of ventilation strategy, which provides dilution of that source. Then we can do filtration, ideally, And be conscientious about what you're putting in your house, too. Another quote from Joe that I love: dilution is not the solution to the indoor pollution. We want to remove it first, right, before we try and dilute it. Common sense, but still, brilliant. Okay, thanks, Joe. There's Joe. So first, remove the source, right? Okay, this is a house that has in-slab ductwork. How many of you have houses that have that where you live? Ductwork in the concrete, in the slab, okay? Do you guys ever pull the grates up and look in the ductwork? I see a couple hands, okay? Yep, I think that's a good idea because you never know what's in there. We all love a little dead rodent-infused air. Or sometimes you'll have standing water in there. Who needs a whole house humidifier when you just have standing water in your ductwork? Or if you've got, air handler and ductwork in an attic space, and you've got insulation on the floor of the attic, a lot of times that ductwork is not air sealed very well. If it's not air sealed, all that conditioned air that you're breathing, you're losing to the attic, but also you can be pulling air in through leaks and cracks and gaps. Anybody recognize what type of insulation this is? Vermiculite, which in my neck of the woods, a lot of times it contains asbestos. So now you're breathing that in. How much is a MERV 13 filter going to help a client in this situation? Right? First, remove the source, then we can talk about filtration. Remove the source. Mold, whole house humidifiers, again, people love their humidifiers. And even tuck under garages, like where people store chemicals and paints and all of that. A lot of times these spaces are not perfectly separated and sealed from the conditioned living space. Okay, so then we use ventilation, try and move that air, dilute it. Sometimes it works well, sometimes it doesn't. These are all examples of failures if you haven't noticed. When ventilation is not working the way that it should, right? How many times do we see perfectly installed ductwork that's airtight, delivering air to where it should be? They've done the manual J's, it's well balanced, every time, right? Yeah. Okay, yeah. Ductwork that's installed right underneath the hot roof deck. We've got condensation issues. Okay, and lastly, filtration, or just complete lack thereof. Hey, they're trying. Yep, they're trying. Or they're not trying. They've just completely unplugged their air exchanger. Okay, so talking about ventilation, there's different strategies, different types. And depending on where you live, when the house is built, what the codes are, you'll see different things. But in general, there's kind of three categories. You can have exhaust-only ventilation, which is like a bath fan or a kitchen fan that suck air out of the house. You can have supply-only ventilation, or you can have balanced ventilation, which is provided by something like an air exchanger, an energy recovery ventilator, an ERV, or an HRV, heat recovery ventilator. So, like I said, just depending on where you live, what climate you have, there's different strategies. Okay, so exhaust ventilation, usually it's simpler and cheaper to install. Right, especially if you don't have ductwork in the house already, you can put in a bath fan, vent it to the outside. That works well. But if you've got a hot, humid climate, remember, for every little bit of air that leaves the house, more air gets pulled in to replace it. Your house is not a vacuum. So you're pulling in hot, humid air to replace the nice conditioned air that you're cooling if you've got exhaust-only ventilation. So a lot of times, the best solution is some sort of balanced ventilation, where you're bringing fresh air in, and then you can also filter it, and there's a heat recovery core on the inside too, and you can manage the humidity levels as well. So that's what we're seeing. That's what you'd want to see in a lot of the newer construction or houses that are older and being remodeled and being made more airtight. So this is an example I'll see up in Minnesota a lot. Before a code started requiring balanced whole house ventilation, houses were built pretty airtight and they started having moisture problems. So they required continuous run bath fans, continuous run exhaust ventilation, which, as you can imagine, can create all sorts of problems too. But anyways, you're pulling in whatever outside air is whatever climate you're in. So ventilation, exhaust only, is not necessarily, moisture control either. So you have to be conscientious of that. So the key takeaways from IAQ, okay, eliminate the source, provide ventilation and filtration. Tight homes definitely need some sort of ventilation, and ideally probably some sort of dehumidification system as well. We're seeing more and more of that. You control the moisture, you control your risk, And a lot of times, some of these small improvements, like upgrading an older style furnace to a high efficiency furnace, can create potentially bigger issues. So what can we do as home inspectors? We can recognize these warning signs, we can educate our clients, and we can recommend further evaluation if we think there's cause for concern. And the last piece here, before we move on to case studies, I just want to talk about comfort, durability, and efficiency. This is what makes a house high-performance house. Again, this is beyond our scope as typically as home inspectors, but have you ever met a client that doesn't care about these things? They just assume when they're getting a house that it's going to be comfortable and it's going to be durable. It's not rotting and it's not moldy. And ideally they hope it's efficient too, but a lot of times it's not. What causes these concerns? Okay, well, you can read this list. Lots of different problems with houses. Most houses have these issues. Hot, cold rooms, humidity issues. What creates a lot of these complaints? A lot of times it's problems with insulation, problems with air sealing, problems with HVAC, and ultimately it's the building envelope too, which comes back to misaligned thermal and pressure boundaries. Okay, what does that mean? Okay, a thermal boundary, another technical term for basically the insulation, okay? The insulation where it stops the heat flow. We call that the thermal boundary. There's also the pressure boundary, or you can call it the air barrier, and that's where the leaks should be sealed, okay? When these things are not aligned, thermal boundary and pressure boundary, when they're not aligned, when there's gaps between them, that's when we have problems with heat, air, and moisture. That can lead to mold, condensation, durability problems, IAQ, comfort. Okay, so what does that look like? Here's a picture. It shows you. This yellow line is the thermal boundary. This defines the conditioned living space from the unconditioned outside space. So if this house is, let's say it's wintertime and it's being heated, okay, we want to keep all the heat in. We don't want it escaping. So we've got our thermal boundary. We have to decide where we're going to put that insulation. And we also want an air barrier because air can move right through insulation, right? So insulation is not necessarily an air barrier. So what is an air barrier? It could be as simple as drywall that's been taped and mudded. That can be an air barrier. As soon as you cut a little hole in it, though, it's not an air barrier anymore, right? And we can have warm, humid air leaking through that, or vice versa if you're in a hot, humid climate. So this is very, very crucial to having a high-performance house, is having a consistent and continuous thermal boundary and pressure boundary. And we call it in building science the building envelope. So thinking about this house, I always like to think, okay, where is the building envelope? Okay, well, on this house, we've got it right across the ceiling. And it's nice because you can physically crawl up into this attic and air seal all the penetrations. And you can make it a nice, consistent air barrier up there, pressure boundary. This house gets a little bit more complicated, story and a half. What are we going to do with these side attic spaces? Are we going to keep the thermal boundary up against the roof deck and make this a hot roof? Or are we going to treat this like it's unconditioned outside space and have ventilation for it and put the insulation on the back of the knee wall and the floor? Either way, a lot of times what I see is confused spaces. People put insulation on the underside of the roof deck and the knee wall on the floor. Like, oh, 3 is better than 2, so I'll just do it all. No, you have to think through these things. Okay, what's inside and what's outside? Same thing here. It gets a little bit more complicated. And this, whew. That one's really complicated, right? That building envelope is complex. So complex homes can equal greater risks. If you've got dormers, bonus rooms, tuck-under garages, cantilevers, sunrooms, crawl spaces, all those areas make it difficult to have a consistent and continuous air barrier and thermal boundary. So one question you can ask yourself when you're inspecting, okay, does every room have some sort of heat or cool supply to it? Is there an aligned and consistent thermal boundary and pressure boundary here? What do you think about this? They're probably going to have some home performance issues with that, right? Yikes. We've even got supplemental cooling here. They need it because their thermal boundary and pressure boundary is really hurting there. Okay. Crawl spaces create their own problems too. And I'm going to kind of breeze through this too, but a lot of times vented crawl spaces are what we see out there, and They're not really inside, they're not really outside. We might have mechanical systems running through them. So is that air mixing? We'll have air leakage, inconsistent thermal boundaries, potential for condensation and moisture. So they can be a big challenge to deal with. And like I said, big source of moisture, air quality, indoor air quality concerns, energy efficiency concerns, comfort concerns, radon, soil gases coming back up into the house. In a perfect world, we see this, but I didn't have any examples of that from the field, so I stole one from U.S. Department Building America Solutions Center. So ideally, it would be, in most climates, encapsulated, where we seal that dirt floor, we insulate around the perimeter, and we provide some sort of conditioned air to the space and dehumidification as well to keep it dry and conditioned. Okay, so the takeaway from this, simpler is better. Keep the inside in, keep the outside out. Okay, let's get to the case studies here. So, case study number 1. This is a house in Minnesota. A client came to me because she had this mystery musty smell, could not figure out where it was coming from. House was built in 1978. So let's take a look at the exterior. Think about moisture management, water management. We do have gutters, that's great, but grading's not great. It's negative, not positive. It's negative, sloping towards the house, pretty flat in a lot of areas. We do have downspouts, but they're clogged. Gutters are clogged. Okay, in the basement, we have insulation in the ceiling. Now, why would we want to separate the conditioned living space from itself? All right, the basement, upstairs, it's all part of the conditioned living space. When we put insulation between them, we're separating them. We're isolating that basement from the heat. You'll see in more pictures I have here, they've actually blocked off their heat registers too. So now that basement is very cold. It doesn't have much heat getting to it at all. They've got some rooms blocked off. You can see some of the basement. Most of the basement was finished. You can see the sheetrock is wet, starting to crumble. In areas it's actually crumbling. She let me kind of poke around in there, and I could see behind the drywall was a poly vapor barrier, and behind that is craft face paper bat, so that's a vapor barrier too. So we have double vapor barrier right up against the concrete foundation from a 1978 house that doesn't have waterproofing on the foundation and has negative grading. Okay, we also have combustion air intake that's been blocked with insulation. There's their combustion air intake. Also notice we have a natural draft water heater and high efficiency furnace with a blocked, combustion air intake. Okay, no supply registers, as I mentioned before. Or wait, I guess there's one, but it's been sealed shut. No bath fans, no kitchen exhaust fans. And it wasn't that cold outside that day, but there was tons of condensation. Even on the frame of the window, there's condensation. Okay, and then also interesting too, open core concrete block foundation. So that's just open to the wet soil below, so all that moisture can and radon can migrate through that open core and come up into the house, into the conditioned living space. So putting all this together, we have no ventilation, no bath fans, no kitchen fans, combustion air is blocked, heat supplies are closed, we got double vapor barriers on a below grade wall with poor exterior water management. They also did spray foam in the rim joist. Right? Thinking it's an upgrade, we're going to make the house more energy efficient, more comfortable. We'll put spray foam here, seal up all the leaks, make it more airtight. She also told me they had an additional person move in the last year, her boyfriend, adding to the moisture load in the house. The gutters and downspouts were new within the last year, even though they're clogged. They weren't there before. They also put new windows in, much more airtight windows, and new siding. And she told me the AC kicks on and off real fast. It runs for a short period of time, then shuts off, which can be a sign that it's oversized potentially, and so it's not running long enough to get the humidity out of the air, so it feels cold and clammy to her a lot of the time in the summer. So what's the diagnosis? Okay, big picture. We've got reduced air exchange. She made the house tighter by putting in new windows, by air sealing the rim joist, and also closing off that combustion makeup air. They increase their indoor humidity by adding an extra person. They have poor ventilation. They don't have any exhaust ventilation. Poor airflow. All the supply registers are sealed off, blocked. potential oversizing of the AC, no heat getting down to the basement. They've got a wet foundation with a double vapor barrier, and trapping that moisture that wants to go from wet to dry, more to less. It can't dry to the inside anymore. Okay, so what do we have? The perfect storm. Yeah. Okay, what's the solution holistically? What do we do? Where do we start? Number one, remember, remove the sources. So if we've got this musty smell, okay, let's get rid of all the things that could be trapping moisture. So I recommended, okay, I'm sorry, but you got to remove all of the insulation, all the sheetrock against this foundation wall. It's getting wet. It is wet, right? Remove the source, and then ideally, let that basement wall stay unfinished so that moisture can dry to the inside. And don't refinish it ever unless you can monitor it and you never have moisture problems ever again. Then you can finish it. But if you put some sort of material over top of it, you're reducing the drying potential and you can trap moisture again and then you can have mold. So if you're okay with that risk, fine, you can finish it. If you don't want mold, don't finish it. Okay? We also need to, hand in hand with that, improve the exterior water management. We should add some sort of ventilation strategy for the house and monitor the indoor humidity. Remove that block in the combustion air. Open up the supply registers and remove the insulation from the basement ceiling so we have heat and airflow circulating in that basement. Remember that psychrometric chart that showed the temperature and the humidities? So let's increase the temperature, let's decrease the humidity so that we don't have condensation issues that are as likely. And then I recommended too that if she continues to have smells, to install some sort of whole house ventilation strategy as well. And then lastly, but not leastly, be aware you've got a natural draft water heater too. And it wasn't backdrafting that day, but it potentially could at some point. So the smart thing would be to replace that with either a power vent or electric or something like that, or a heat pump, so we don't have to worry about backdrafting. So as you can see, it's not always cut and dry, simple, black and white, right? We got a lot of things going on here. The house is a system. You change one thing, you impact another. We need to think about it holistically. That moldy, musty smell is coming from a lot of different things, right? And we need to tackle all of them to fix this problem. Key lessons, like I just said. The house is a system. Order matters. You need to make sure you've got proper ventilation before you start air sealing the house. You need to make sure you fix your water issues before you finish a basement. Think about backdrafting, and then think holistically when you're doing these improvements. My building science professor at the U of M, Pat Hellman, he used to use this analogy about kind of thinking about the success or failure of a house in terms of how close it is to the edge of a cliff. And he used to say that it's easier, cheaper, and faster to push that house closer to the edge of the cliff than it is to kind of think holistically and do all these things. How many people want to replace their water heater when they're talking about making it more energy efficient and air sealing and insulating their attic? Nobody, right? But as soon as you air seal that attic and you add more ventilation, now you've got a backdrafting problem. So again, we need to think holistically and understand that these incremental improvements can create unintended consequences if we're not careful. Okay, case study number 2. House in Minnesota, built in 1924, beautiful house. Clients came to me because they had extremely high utility bills in the wintertime. This was back in 2023. They were spending like $800 a month, sometimes more, on heating. And so their goal was to improve the energy efficiency while still maintaining structural integrity and property value. Okay, a little bit of background info on this house. The clients were not aware of, they also had comfort issues. They were complaining about certain rooms being really cold in the winter, drafty. They were not aware of these issues when they bought the house and they had a home inspection. They're like, why didn't my home inspector tell me these things? Okay. Yep, and then they also have spent their entire budget already on piecemeal, quote, improvements. Some, actually, I found out later, adding to their utility bills. Okay, and so they wanted help prioritizing these, remaining repairs and maintenance things that needed to be done based on whatever little budget they had left and potential return on investment. So here's a list of the improvements they did to this house when they moved in. They had water intrusion from an ice dam the first winter they were there. So what they did is they gutted that room, took it down to the studs, put new sheetrock in, new ceiling to deal with all of the water damage. They added, that room was the cold room as well, so they added an electric baseboard heat to supplement the heat to that space, make it more comfortable. Here's a picture of that room. So they had ice damming here, water intrusion, and then they added electric baseboard heat to it. This is the room. All new interior and new electric baseboard. Okay. They also added another bathroom upstairs for convenience with a laundry room. So here's their bathroom. Which cost a big chunk of change. They relocated and installed a new electrical panel. That's nice. Okay. They added, quote, in-floor heat to their kitchen breakfast nook. I'll show you what that was in just a second. And when that didn't work, then they added electric baseboard heat as well. So that kitchen nook is right below the office, so all these rooms are cold. And their plumber came and said, well, I can put in some in-floor heat. He just ran some pipes right through the floor joist, hoping, I guess, what is this, radiant heat transfer would make that floor warm. Well, when that didn't work, then they added another electric baseboard. Okay. They also did spray foam insulation to their basement. They wanted to finish their basement. Yay for them. They had to put on a new rubber membrane on the back porch flat roof. We haven't had rain in like a month. And they installed a metal ceiling under the deck to collect rainwater because they didn't like dealing with ice when they were trying to get out to their cars. So that cost them a pretty penny too. They repaired the rotted wood on the back porch underneath all of that water that's sitting there, although, quote, I say repaired it, bondoed it and painted it, but still wet, still leaking. They had to replace an AC condensate line because it clogged and it overflowed and it damaged the ceiling. They had an AC unit in their attic. They had to replace a dryer duct because it was flex duct, went through the roof. So here's a picture of their attic, air handler, ductwork, dryer vent, and then we also have the condensate line that leaked and overflowed, damaged the ceiling. So additional information from them too. They've got a very complex house. Here's some pictures of that. Sunroom, bump outs, flat roof, dormer, little AC up on the very tippy top dormer. That's not typical for Minnesota, by the way. That's a retrofit situation. Remember, it's cheaper, easier, and faster, usually, and that's what people choose. So they wanted AC in this house. That's where they did it. They put all the ductwork in the attic. So we've got an attic space here, one that's accessible. We've got an attic space here that's not accessible, an attic space here that's not accessible. We've got a tuck under garage. We've got a flat roof. We've got a lot going on with this house. It's a complex house, right? Thermal boundary, pressure boundaries, very complicated. And also, we don't have any insulation. You can walk right up into the attic. And you can see we've got roof vents here too. So they didn't need any ventilation in their house. When it's super cold outside and they burn something when they're cooking, it just goes right up the stairs, right out through the roof vents. Right? Their house is just leaking air. Okay, they also had a bucket underneath this. Turns out that little dormer with the AC unit on it, it's leaking. So we've got rot happening underneath that guy. Okay, and on top of it, this was interesting. This is kind of unusual. I noticed in the attic, I could see the exterior wall, and it didn't look like a typical wall. Got closer. Turns out their house was built with structural clay tiles. And they just have lath and plaster on the inside of that. And it's brick on the outside. So it's a big thermal mass. It takes a while for it to heat up, so it stays nice and cool in the summer for a while. But in the wintertime, super hard to keep heat in and to make it feel comfortable, right? There's no insulation in that wall. Think about the thermal bridging we saw with the studs. Our whole house is a giant thermal bridge. Okay, that's kind of what a typical wall would look like. So that was unusual. And then they've got these heating and cooling systems that are technically kind of outside the thermal boundary as well. So their comfort and efficiency suffer because of this. Again, ductwork in the attic. This is going into the garage, the tuck under garage, and we've got hot water pipes from the boiler taking heat through the garage, which is a garage supposed to be heated. usually not this way, not unintentionally, but these hot water pipes go to that sunroom that was off on the side. So we've got to get heat to that space. So here we go. This space is also kind of getting ambient heat, and the room above it's cold. Additional observations. Okay, again, the roof leaks. We've got an 18-year-old natural draft boiler. We've got a natural draft water heater. We've got an older AC unit. The water softener's not working. They've got water draining into their garage. That's starting to damage their structure. They've got old plumbing that's corroded in the upstairs bathroom that's leaking, so they don't use it. They've got an ensuite bath fan, but that's the only ventilation they have for the house. So just thinking about combustion safety and IAQ issues, if they decide to air seal the house and make it more energy efficient, more airtight, we might have potential air quality problems, moisture problems. And also I heard from them just recently that they also had water coming in through their finished basement this spring too. Oh, what a nightmare, right? Oh my goodness. Okay, so their main goal was to reduce utility bills. We've got this complicated building envelope, whoops, with all these tuck under garages, walk-up attics. We've got heating, cooling systems going outside the thermal boundary. We've got electric resistance heat, which is us adding to the bill because we don't have proper insulation and air sealing for these spaces. We've got no access to some of these attic spaces, so we need to create. And then we've got structural clay tiles. So, in general, you know, they had no clue when they bought this house that it was going to cost them so much money to heat and cool. It was going to have so many comfort issues. And they had an inspection done. But I'm just saying, as inspectors, we can look at these things. We can think about the thermal boundary. We can think about where the insulation is, if it's air sealed, if there's going to be comfort issues potentially, and talk to a client. And we don't know for sure, but we can say, well, this house is built a little bit differently. We don't have proper insulation and air sealing, you know, and so warn them about these things. So what I told them, okay, I know you want to reduce your energy bills, but the number one thing we need to focus on is the structural integrity of this house and the durability of it. And we've got active water leaks coming in, bulk water, right, which is our number one concern. So we need to address that first. So let's fix the water leaks happening on the flat roofs. Then we can think about potentially improving the building envelope, right? And if we air seal and we insulate, well, you may not need these additional sources of heat as well. It changes, you know, the loads of the house. And so that might be good because you're going to be up for a new boiler soon. Let's budget for that, amongst other things. And we also need to think about, if we're going to seal up that attic or make it more airtight, we don't have really any ventilation for the house. So you're going to have to think about adding some sort of ventilation strategies as well. And you can't really just do one thing, ideally, without doing all of these things, right? Otherwise, you're just going to create more unintended consequences and problems. So we have to think about it holistically. If these people, these homeowners, go to just an insulation contractor, the insulation contractor will gladly insulate their house. Are they going to talk to them about backdrafting combustion appliances? Are they going to talk to them about lack of proper ventilation inside? No. So then they'll suffer with potentially carbon monoxide or mold or moisture, right? So who is looking at the house as a system and giving people kind of this general information, educating them so that they can make smart decisions? So these piecemeal upgrades lead to bigger risks. More heat, more comfort. Fix the envelope first. Better envelope means lower bills, but it could lead to IAQ issues. Recheck the mechanicals and ventilation if you're going to do the building envelope first. And plan these improvements as a system. Okay, that was a lot. We still have a little bit more time. Good, because I've got 2 more case studies to breeze through. This one's much shorter. Okay, but still just as depressing. Okay. All right, case study 3. This is in Indianapolis. This is a client that came to me because he noticed his wall was soft, right? Remember the image I showed you earlier of the hidden mold? Okay, so he wanted to know what the extent of the problem was, what caused it, and what does he do about it. So here's a picture of the house. This is the south wall. So this is south, that's north over there, east, west. And the rooms that he noticed the soft wall was actually this room right here above the garage. He's got comfort issues. This is his at-home office. And his desk was against this wall, and he would rest his feet against it. And one day he dropped his pen, went down to pick it up, and realized that there was a divot in the wall where he rested his feet. So he pulled back the baseboard and saw all this mold, which got him curious, and he made a little hole in the wall, and that's when he saw this mold. So he called a mold remediation company. They came out, they opened up this wall, and I'll show you some more pictures. Here's the back side of the house. So we've got brick veneer, we've got hardy board. Here's the inside. Here's what that looked like. Oof, pretty extensive. Now, we've got a lot of moisture damage on the OSB, kind of underneath the windows, but it was over the entire wall as well, behind the baseboards. Now, some of this house actually had a vapor barrier. Not all of it did. So some of it was potentially finished at a different time. I don't know. Same thing's happening here. And this is also on the south side, behind the brick, on another bedroom upstairs. So it's pretty extensive. I asked him, I said, did you have an inspection done? Yeah, we had an inspection, and actually the seller had an inspection, so he sent me the seller inspection report. And this is kind of the exterior part. I just want to read this. The brick, the inspector mentioned the brick windowsills are installed with minimal fall and have deteriorating mortar joints. Okay, so in these pictures you can see like little places where water can get in. Tops of the porch posts are not finished. Hardboard siding has no relief to the wall, blah, 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 blah. It wasn't installed proper. Due to these improper installations, there are deteriorating boards. Okay. And then talking about some other things, exterior photos. So here's some pictures, examples, I guess, of that exterior siding that's not installed properly and starting to deteriorate. Okay, that was it in the report, kind of pointing at what might be problematic. I asked for the inspection report he had done too, and so he sent that to me, the one he paid for. And this is what the action items were for this house. It was talking about a furnace gas pipe that had a condensate drip leg that appears to be missing. Flexible steel gas piping at second floor furnace is bonded to the electrical ground, had a safety concern. Talked about the height of the kitchen countertop outlets. Talked about a plumbing vent that was not flashed properly. Okay, those were the standout items on that. Disappointing, I would say. Consideration items. Okay, there are areas of deteriorated siding. Further evaluation is and repair as needed. They also mentioned steel lintels over the windows and door openings that should be painted. They also mentioned some minor cracks in the brick. Repair is needed. Blah, blah, blah. Minor deterioration of the trim at various areas. Have it further evaluated and replace as needed. Okay. That's about as far as that goes. Nothing else has to do with exterior. So here's the pictures. Again, they're showing kind of the same deterioration of the siding, rusty lintels, some cracks in the brick. Same thing. Just some areas of deterioration. What are we missing here? Kick out flashing. Look at how rotted that is. And we've got brick right below it. Do we have any, proper drainage happening at the bottom of that wall? Probably not. Okay, so my recommendation is there's probably a lot going on here. Remember that image of Vapor Drive with a brick wall? Okay, we've got a climate that both has heating and cooling. It's Indiana. He noticed this condensation happening on the inside behind the baseboard and at electrical outlets on these exterior southern walls when it was really hot and humid outside. So imagine, okay, we've got a hot, humid climate outside. We're air conditioning inside. Which way does that moisture want to go? From more to less, from hot to cold, right? And if it rains and it saturates that brick on the exterior and the sun comes out, which way is that vapor going? Well, it's drying to the outside, but it's also going to dry inside, right? And so that moisture can be pushed through that wall assembly and condense on the backside of that sheetrock. But then on top of it, we're also seeing areas where we're missing flashing details, kick-out flashings, the brick isn't installed properly, and so I've got bigger concerns, potentially more than just vapor drive, that water was getting in other locations and creating some of that catastrophic kind of hidden moisture damage. So my recommendation was we need to conduct further investigation and figure out what other areas have problems and not. We need to number one, address exterior bulk water intrusion that's happening in this house in several locations. And then we also need to somehow figure out this vapor drive issue, and maybe, I don't know what that solution looks like. Is it taking the brick off and putting a different type of siding on? I don't know. That's beyond my level of expertise, but I can see that there's potential multiple ways that moisture is getting in to these walls and creating problems. So even though it's newer construction, we've got a mixed humid climate, improperly installed and maintained exterior cladding, creating all these moisture problems. And luckily, he wasn't wanting to sue the inspector, but the inspector said, well, you got some deteriorated siding, have it repaired. And that was the extent of it. No weep holes, no weep holes. Yep, question? Yep, no weep holes. 2003. Yep, 2003. Yep. That house was the house that they had to replace all the PEX plumbing as well, so we already had the interior completely gutted. Yep. That's an expensive mistake. Okay, and then very quickly, last case study. This is a house in St. Paul, 1920s. A client had water dripping through their ceiling in the middle of winter, and they wanted to figure out why it's dripping in. Is this a roof leak? Is there something else going on? Don't know. And then how do we fix it? So let's look at the house. First thing we notice about the building envelope, how would you describe it? Is it simple or is it complex? Pretty complex. Okay, let's see if there's potential places where water can get in. Number one, is it bulk water creating an issue? Well, potentially. Little slits, places, flashing details, not great. Okay, here's what the inside looks like. We've got some slants happening because it's kind of like a 1.5-story house. Now, what was interesting is they recently did an upgrade, quote unquote, improvement. They added spray foam to certain areas. I say certain areas. This was spray foamed. This was not. I could literally stick my hand up there and touch the roof deck in these areas. So the areas that were kind of easy to get to, the spray foamers came in and sprayed it. The areas that weren't, they didn't do anything about it. They didn't remove lath and plaster or sheetrock. They didn't remove roof decking. They just did the inaccessible, unfinished areas, okay? So would you call that a consistent thermal boundary and pressure boundary then? No. Okay, they've got water staining in lots of locations. Water staining. Did some IR imaging. Lots of cold spots too. And this client, I asked some questions. I'm like, okay, what was the scope? Well, they added spray foam to the roof. Well, where? Well, the whole roof. I'm like, did you remove any roof deck? No? Okay. And then you can see, obviously, we've got thermal bridging happening, lots of heat loss happening on these slants. So they were frustrated because they still had ice dams, too. Even though they paid to have the spray foam done, they were still having ice dams. And now they're having water dripping in, too, on top of it. So you can just see all the inconsistencies in the thermal boundary, pressure boundary, all these cold spots. And this is without a blower door, so this is just normal conditions. Okay, let's look at the mechanical system. So looked at the building envelope. We have a brand new high-efficiency boiler. So we used to have a natural draft boiler, one that would use air from the room, from the house for combustion. And now we have a system that's sealed. It's pulling in air directly from the exterior and exhausting directly to the exterior. So that natural air exchange that used to happen with the old natural draft boiler is no longer happening. So all of that moisture that's being generated from cooking, showering, living, they had a big family, is staying in the house. And on top of that, we added closed-cell spray foam to certain areas that make the house more airtight. Oh, no one cared about that, though. No one thinks about the poor little water heater in the corner. We have lots of condensation on the windows. It's not even that cold out. What's missing? No bath fans. More information they gave me. They have newer windows in the last few years. They also don't have any exhaust ventilation, no bath fan, no kitchen fan, which is typical for like a 1920s house where I live. They also stated that the water staining appeared during cold weather. That was key. I was like, is the water showing up after heavy rain? They, lived in it for a season. Like, no, we don't see it after heavy rain. Okay, it's only showing up in the wintertime. I asked for, they actually had the paperwork from the spray foam contractor, so I asked to see that. I did my best to read it. Here's what I think it says. Foam insulation in all exterior walls of upstairs space and ceiling. None in area below windows in master bedroom. Also, putting foam in ceiling of living room Roof space on front side of house, crawl spaces included. Sure didn't look like that with the IR camera. And they didn't remove any of the lath and plaster. So I don't think that's true. That's just my guess on that. So let's take a step back. Let's look holistically what's happening to this house here. They tightened up the house by air sealing the accessible attic spaces with closed-cell spray foam, and they put in newer windows too. They reduced the air changes by replacing that old boiler with high efficiency condensing boiler. They don't have any mechanical ventilation. The thermal and pressure boundaries are not consistent and they're not aligned. So, unintended consequences? Potential air quality issues, okay? So we might have a backdrafting water heater. We have excess humidity that can lead to mold and moisture issues. We also have potential durability and performance issues. We've got these attic air leaks that are still happening where warm, humid air can get up into these attic spaces and these cavities and condense on the underside of the roof deck. And that moisture can accumulate in the voids, and we can start to rot out our roof deck as well. And they still have ice dams, continued ice dams. So the unintended consequences of, quote, improving this house, putting in a higher efficiency boiler, adding spray foam, adding new windows, on paper, it looks great. In reality, it became a nightmare. We've got water dripping in from the ceiling, potential rot issues, increased mold and moisture, and potential combustion safety issues as well. So what's the holistic solution? Reduce the humidity in the house, number one. We want to try and reduce the humidity, install point source ventilation, kitchen, bathroom, use that ideally. With that, we need to replace the water heater. That's only going to make that thing potentially backdraft more. And ultimately, the solution is improve that thermal boundary and the pressure boundary. Although to find a contractor who can make that perfect is going to be a real challenge, and it's not going to be very cost effective because it's going to involve removing interior finishes or the roof deck, and the roof was in pretty good shape. So the advice here, let's start with the low-hanging fruit. Let's see how that affects things. If we can reduce the humidity inside the house and keep it drier, hopefully we can reduce the amount of condensation that's happening in the attic spaces as well, and we keep that to a minimum. Cross our fingers, it's an old house. We've got original roof decking that it can handle getting wet as long as it can dry out, right? So, key lessons: inconsistent thermal and pressure boundary plus air leakage plus high humidity equals moisture and condensation at the roof deck in wintertime. I see your hand, 1 second. Combustion safety and improved ventilation strategies should be used before they tighten up the building envelope, ideally. And then this poor spray foam application and scope of work can create these performance issues as well. So, real quick, I'll get to your question, just wrapping this up here. Review: heat goes from more to less. Air pressure goes from high to low pressure. Moisture goes from wet to dry. We want to control these things to have high performance. And we've got all these different parts and pieces that impact one another, these dynamic systems, right? The occupants, the materials, the design, the climate, and the construction. And so we understand that as home inspectors, right? And we're going through the house. We're looking at all these systems. Can we step up our game a little bit? Reduce our own liability. Find these things that are maybe not necessarily on the surface or a checkbox. Build your client trust. Improve your inspection outcomes. Again, it's kind of pushing you outside your comfort zone, which I guess Mark and I are on the same page, again, from his speech this morning. Let's step outside of our comfort zone. Let's think in systems. Look beyond the obvious. Talk to your clients. Ask them what matters to them. Make sure that you are addressing any of the concerns that they have. And lastly, again, protect yourself and your client. Go beyond the defects. Try and explain risks. Translate these symptoms that we're seeing into causes. Build trust. Show them the whole picture of what's going on. And I challenge you to try to think in terms of the house as a system and implementing building science into your next home inspection that you do. So if you have any questions, I'll stay here. There's also, I just want to let you know, if you've got more questions or you want to know more about building science, Ruben and I do a podcast. It's called Structure Talk. You can check that out. And if you scan the QR code down there, you'll get my contact information. So feel free to reach out if you have any questions, and I'll stay here and answer questions. So thank you. Okay, there was a question in the back. Did you have?
Yeah, real quick, just that outside, you said there was no air fan, heating fan, but say if it did have one, just turning that on and running it consistently always.
Yes, it should because Minnesota is dry in the winter, right? You're pulling in cold air. Cold air holds less moisture. So if you're running those fans, exhausting the humid air that's stale in the house, you're exhausting the humid air. You're pulling in cold, dry air. In theory, that can help dry out the house, and that's when they're having the problems. Is the winter time. Yep. Good question. Okay, question in the back. Yeah. Sorry, it's so bright. Yeah. Yeah. Yeah, 10 to 25, depending on how they frame it. Yep, 10 to 25% thermal bridging, which, depending on the house, I mean, I guess, how do you define it's a lot? I don't know. Yeah. Yeah. It's tough. Yeah. 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 Sure. Yeah. Yeah, typical spacing, you can get between 10 to 25% of the heat loss through a wall through the thermal bridging. So you stop that by having some sort of continuous insulation, on the inside or on the exterior. Typically, the best is on the exterior to try and stop that, reduce it. It's usually not cost effective unless you're already replacing siding,
And then my area, I would say 90% of the houses have basements,
Uh-huh.
and 90% of the houses were built pre-1980,
Yeah.
and they've all got finish basements.
Same thing where I come from. Yep. Yeah. The reality is there's a very high risk for mold and moisture. And some clients don't care and some clients do. So know your client. If mold and moisture is a big concern for them, well then educate them on how moisture comes through this foundation, how it gets trapped behind here, and you can have mold with it. It's as simple as that. You don't have to say there is. You don't have to say remove it. You can say there's a higher risk for moisture back here. Are you okay with that? Yeah. Yeah. Good question.